So here I want to make some remarks kind of justifying our interpretation of curl. So if we've got a vector field F, this is a terrible drawing of a vector field, but we can understand F I guess we want to understand the curl of F rather. We can understand the curl of F by considering the dot product of curl F with various direction vectors P. For instance, if just by taking P to be I, J, and K, this would tell us the components of the curl of F, so that would completely describe the curl for us. But we want to just pick some direction vector. So let's say this is a unit vector, and then the curl of F is doing something else. Let's say. So if we want to understand the curl of F dotted with P, let's say we want to understand this at some point Q. Well, we can consider a small disk centered at Q and orthogonal to whatever direction vector we're choosing. So the value at Q will be approximately the average value over that disk. So if we call this D, let's say this is D rho. Rho is the radius of this small disk. So the average value of this over the disk is we integrate P d sigma, and then we divide by the area of the disk, which is pi rho squared. And when rho is small, this average value will be approximately equal to the exact value at Q. More precisely, we can say that this the exact value will be equal to the limit as rho goes to 0 of this. Now, the reason we introduce this is that now we have an integral over a surface, so we can invoke Stokes' theorem. So by Stokes' theorem, this is 1 over pi rho squared integral over, let me call the boundary of this C rho for just a circle of radius r, our radius rho. And now circulation of the original, now this line integral of the original vector field. And we interpreted this sort of integral as measuring circulation. So essentially, if you believe our interpretation of this of this type of integral as circulation, then this value of the curl in a particular direction is going to be related to this. There should be another lim in here. Is going to be approximately equal to the circulation of F around a small disk, or sorry, a small circle of radius rho, and then divided by pi rho squared. In fact, if we just look at the left-hand side of this equation, so this, we know that this dot product will be maximal when this direction vector is parallel is the same direction as nabla cross F. So this is maximized by maybe I should say when our direction vector is equal to the direction of the curl of f. This is at the point Q. So we could take this circulation, again, we could measure this circulation around a circle in any direction, but the circulation is maximized when we take the direction to be the direction of the curl. So that's why we're saying that the direction of the curl tells us the direction of rotation or of circulation. Okay, so that sort of explanation for the direction part of the curl interpretation. The second part was in angular velocity, so something more precise. So for that, let's just consider the basic rotational vector field. So we've got an angular velocity. So F is omega negative yi plus xj, where omega is the angular velocity of our rotation. So this is sort of the basic type of rotation, and so we want to see what the curl is measuring in this case. So curl F, and this will just be a planar vector field, so we'll only get a k component. So this is 0, negative omega y, and then omega x. So this is something times k. This will be omega here minus omega, so we get that the curl is given by 2 omega k. So in general, we said the direction of this tells us the direction of rotation. The magnitude of the curl is not the velocity, but it's twice the angular velocity of our rotation or circulation.